Welcome back, everybody. Welcome back to the channel. So today we're going to be doing a quick intro to our multi-threading system. Now this is going to be a multi-threading system that is based off of the Dalvik virtual machine. So there will be some similarities there if any of you guys have looked in the code. Now this is going to be mostly just a basic look at our threading system. It's going to be a pretty short video. We're not really going to go too much in depth until the next episode. I just want to lay the groundwork so we can see actually what's going on. So let's look down here. So what we want to do is we want to create a couple of defined statements. Now I do think I've gone over some of these, but let's just go over them just to make sure I've gone over all of them. So you want to have an illegal thread ID defined. -1 in my virtual machine is going to represent a illegal thread ID. Now this can be whatever you guys want. It doesn't matter. Just pick a number and make sure it's negative, by the way, because thread IDs are going to have positive ID values. So you want it to be just a random negative number. We also have a thread map size. That's going to be 0x2000. I have no idea what that is. I think that's 4268 or something. I don't remember. It actually doesn't matter. Honestly, this is just another random number. What this signifies is this signifies the width of my map. Now, what I end up using is I end up using what's called a hash map for my threads. So let's say I have, this right here as a list of threads. The reason why I have my hash map to or 4,000 whatever characters, or maybe I think this is actually 8,000, but basically 8,000 thread objects wide is because if you guys have ever used hash maps before, the less items you have in terms of the width of the hash map, as you start to get into high numbers, you start to end up basically having to traverse through tens, if not hundreds, of elements in a single index because you don't have a wide enough array to pick from basically to choose where to put the actual item. So that's kind of why I have a wide or big thread map size. We also want to have an internal stack size. I think we've gone over this. Our internal stack is going to be 1 MB wide. That's going to be the default value for every internal stack in the virtual machine. We want to have an internal stack minimum, which specifies the minimum size of our internal stack. That's going to be 1 KB of memory, just as a minimum. We also want to have our default actual physical stack size. So that's going to be the actual stack in terms of physical memory that our thread's going to use. That's going to be 1 MB. We also want to have a minimum as well. That's going to be 50 KB as the minimum. And then we also want to have a stack overflow buffer of 10 KB. This is a very large buffer, but what this basically is for is this is going to be used for our just-in-time compiler. We need this overflow buffer. What we're basically going to do is, so let's say the user decided to create, I don't know, a thread stack size of 50 or whatever, 50 MB. We're going to tack on an additional 10 KB to that, whatever the user is allocating, in order to create a buffer if anything were to happen in the actual stack, and it's really complicated. We'll see that at a later point when we're actually doing our actual JIT, but after that you want to have three final GCs. So what our basically programming language is going to have is, by default at startup, we're going to have a default of 3 threads running off the bat. So those threads are going to represent the main thread ID, the garbage collector thread, and the JIT thread. And they will have these IDs as follows, and they will always have these IDs. This represents the base level amount of threads that we need to run our entire system. Of course, you can't have all these running on the same thread, so that's why I do it. So now let's actually look at our thread class object. So you want to create a thread object, and you want to create a series of fields. So I have this init here, or this constructor which calls init, which just initializes all of our fields. I'm pretty sure you can understand what each field should be initialized to. So before we get into the fields, actually, we're going to have to create a couple different enums. So up here, oh, okay, so I have what's called a thread state. That is going to be in here in the runtime folder. And this is going to represent all of the various different states of our threads. So threads are going to have several different states in our programming language. They're going to have the created state, the started state, the running state, suspended state, and killed state. The created state is obviously when a thread is created. The starting thread or the started State is basically representing that the thread is starting, but it's not running yet. And that is important. We do actually use all of these states, by the way. Running obviously means it's running. And suspended means that the thread is suspended. So basically, the concept of thread suspension is basically forcing a thread to go to sleep. So you're not killing the thread, but you're putting it, it's like hibernating it basically. So that's kind of what that is. And of course, killed is just killing a thread. Then we also have a couple different priorities. So we're going to have thread priority of low, normal, and high. This is operating system independent, so we just use these values. They can be whatever you want, and we'll just do whatever we need to do to actually set the official thread priority. So the reason why you want to do this too, by the way, is you want to have some consistency because when you're building your standard library here, I also have a file that's in conjunction with this one called, so I have a thread results enum, which basically is in direct alignment with the thread processing results enum, and I also have a thread priority and a thread state somewhere else. I don't remember where I put it, but you want to create these constants so that when you're building your standard library, you can also create the same ones. So we're going to have various different processing results. I don't want to go through them right now. I mean, you guys can read them. They're pretty self-explanatory, and we'll see them as we go along, so it doesn't make sense for me to explain them now. But we have those, and then finally we have a t sig underscore t. So this is going to represent a thread signal. Now, the way that things work in my programming language is I use a concept of signals. And basically a signal represents, it's just a number basically, but basically what it represents is a piece of data telling the thread that something very important has happened and you need to stop whatever you're doing and go handle that signal. So I have a couple different signals that a thread can listen to. It can listen for an exception signal. That means that the thread is in an exception mode. It can listen for a suspend signal, which means to go to sleep, or a kill signal, which means to kill the thread in its tracks. So the way that my signal system is going to work, and it's kind of, I've mentioned this before, unlike Java, if you kill a thread, it's dead on arrival. Basically, once you call that function, the thread is killed and there's nothing you can do about it. So there's not like an event you can listen to, like interrupted exception or whatever. Once you interrupt a thread or kill it, it's dead. So let's go back to our thread class. Now, once we kind of have those basic things set up, we want to create our fields. So I'm going to have a ton of different fields here. So I put a couple of the main fields that are used by the GIT at the very top because I'm lazy and I don't want to do all the math to figure out, where everything is. So I just put it at the top to make it easy for me. But we basically have the calls. So this is going to be how many function calls we've actually performed. We have a couple different stack element items, which are going to be the data stack, which represents the actual stack, and then pointers to the stack pointer and the frame pointer. Those are going to be references that we're going to be using to like manipulate the stack and stuff. Now, a stack element. Now, here's where we start getting into how the stack works on threads. It's very simple, guys. Basically, all a stack element is it's either a number or an object. A number, obviously, in our programming language is going to be var. So the reason why I do this is because it is very easy to access and manipulate those numeric values without having to create an object. Because if you really think about it, if I go down here to like an example, I'm going to go to the syntax.sharp, and if I create a simple for loop here, or actually have a couple for loops here already, and as you can see in there, I basically start at 0 and then I, go for a couple seconds and then I plus plus it at the end. If these stack items were actual elements, like if they were actual objects, it would take a significantly longer time to manipulate each of those objects. So that's why I put double as a var. And then for data structures, I use the object class. The object is just going to be a container that contains a sharp object. We'll go over that in a little bit when we go over the garbage collector, but yeah, this is kind of the basic makeup. So you want to just create a basic object class which contains the sharp object, which I think we've actually talked about the sharp object before. But yeah, so that's going to be how the stack looks. And of course, I have a couple helper functions here as well for doing simple stuff like modulation, because since it's a double, you have to convert it to an int. So I do an int modulation on a stack element, an AND, an OR an XOR. So I have those couple of functions. So once you have your stack element set up, then you want to create a pointer, you want to add a field called current, which is going to point to the current method that we're executing at the current point in time. You also want to create a frame of a call stack. Now, a frame is going to be basically a frame. So the way that our system is going to work is every time when you call a function, you're going to need to create what's called a frame. A frame is going to represent all of the information that is pertaining to the previous function. So a frame is not going to be used for the current function we're calling, it's for the previous function that we're calling. And doing this, like I've said before, it slows down your programming language immensely, but it allows for you to, when you return out of the function that you are in, you don't have any issues because the stack will be completely reset to exactly what it is. So what we're going to need to store is whatever the return address is or the return function. The PC that we were at before we called the function that we're in now, the stack pointer and the frame pointer, and then whether or not this is a JIT call. That's very important because as we start getting into building our JIT, as well as running our Sharp native bridge, if we want to call like C++ code using the language itself, then we're going to have to know if we're in what's called a JIT context. And what that's going to represent is, we'll see it in a little bit, but basically as we're executing our code, we're going to need to return out of the main loop function that executes the source code so we can return out back to a higher scope for, some C++ code or a native function. So there's that. And of course you can see the functions here. I just have an init function and a basic constructor, which sets up the frame. So we also want to have a stack limit integer for just making sure that we know how big the actual internal stack is. We want to have a cache, which is just a opcode instruction pointer, which just points to the actual bytecode that is in the current function that we're executing. So that's what that represents. And then we want to have a PC. So the cache is going to represent the actual pointer to the bytecode for the function we're executing. And then the PC is going to hold the current pointer to the current instruction that we're executing at any given point in the execution. You also want to create a signal. Now this is going to be the tsig_t, and we're going to be monitoring this integer flag to make sure that if this flag is not equal to 0, then we can basically check for that. It's a lot easier and a lot faster to do it like this at the JIT level, because otherwise I would have had to check, have we suspended yet? Have we shut down yet? And it's just a lot more instructions that I'd have to write. So we also have max thread ID. That's going to be used for our hash map. And then we also have a TID. So this is going to keep track of the current thread ID that we have. So as we're allocating threads, this is going to change based on what the new ID needs to be. We also want to create a hash map of int and thread. Now, this is not in the native C++ library. This is actually custom made. I actually pulled this off of I don't remember where it was. It was on some website a long time ago, but that code is 100% custom. So, and it works. I've tested it, so you shouldn't have any issues. And if you guys want to add that to your project, you can just head over to the lib folder. So if I close this, so you can head over to the lib folder, then the util, and it's going to be called hashmap.h. And you can pick that up. It's just a basic hashmap file that has a few functions in there. So this is what I use. So once you have that set up, then you also want to create what's called a recursive mutex. This can be found in the mutex include. It's in one of these files, but it's basically just include and then mutex to actually include that one. And you want to use a recursive mutex. You don't want to use a regular mutex. The reason why is because recursive mutex allows this same thread to relock the same object more than once. The reason why that may happen is because there's situations where it could happen. Trust me, because as we're going to be building this system, there's going to be a lot of multi-threading and synchronization that we're going to have to be doing when we're calling all of our various functions. And you don't want to have that burden of trying to think if you're going to ever have a deadlock exception because a thread ended up locking itself because it called into a function that called another function that was also trying to lock the same object that was already locked before. So just kind of keep that in mind. You also want to create another recursive mutex. So there's going to be two main mutexes here. So we're going to have a global mutex called the thread monitor. We'll see what that's used for later. And then we're going to have an individual thread mutex. So that's going to also be used for something specific, which we'll get into later. Then you also want to have the current ID of the thread, the current stack size. This is going to be the physical memory stack size that we have. st base and st floor. That's going to represent the base address of the stack and the floor address of the stack. So basically the base address is like, so when we actually start the thread, we're going to start at address of 0x, whatever, right? Then we're going to go all the way up to 0x, whatever. So we want to keep track of the base address and the floor address of the actual thread, so that way we don't go outside of those bounds. And these values are mainly used by the JIT, by the way. We don't really care about those at the high level. But yeah, so there's that. You also want to have the thread priority. So that's going to be whatever the execution priority is, whether or not this is a daemon thread, whether or not the thread is terminated, the state of the thread, whether or not it's suspended, whether or not it's exited, the name of the thread, of course, the main method of the actual thread, the exit value, the current thread, args, the exception object, and a rand pointer. This is going to be for generating random numbers. We'll get into that later. We'll get into this data structure when we actually come across it, but we want that. We also want to have, so this is going to be operating system based, the actual physical handle or pointer to the actual thread. So for Windows, it's going to be handle and thread. For Linux, it's going to be pthread_t and thread. So notice I do name the variable the exact same name to make things a little bit easier. So then that's it. And then we basically just have a bunch of other functions. So in the next episode, we're going to get into how I actually create threads, how I manipulate and manage threads, and do all of those various cool things later on. So hope you guys enjoyed the video. As usual, if you have any questions, definitely put them in the comments section below. And of course, if you guys would love to help support the channel, you can always head over to my GitHub repository at andrewdevc/sharp. And when you do, definitely watch, start, and fork this repository. That gives this language a lot more visibility and let other developers know this language exists. Also, if you guys are curious about some of the stuff that I'm looking to add in the future, you can always head over to the project section and you can click on the roadmap, and this is basically going to be the main hub of where I keep all of my various updates regarding the language. So anything in here that I want to do to improve the language or bug fixes, that's all going to be listed here. So you can check it out and see what are some of the cool things that I'm looking to add in the future. So that's going to be it for today, guys. As usual, if you're new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.